Most standard regression models in deep learning are deterministic. Mathematically, they map an input x to a scalar output y. While this works for accuracy, it fails at uncertainty. If your model encounters noisy data or data it has never seen before, a deterministic network will still confidently output a single number, hiding the fact that the error variance might be huge. To solve this, we need to move from point estimates to probabilistic distributions. Today we are going to build a neural network with a Gaussian head. Instead of predicting a single scalar y, we will predict the mean mu and the standard deviation or variance, allowing us to capture the model's uncertainty for every single prediction. To get started, in this case, our goal is to have a model that predicts both a mean and variance for continuous regression tasks. And in this case, we show the mean by mu. Theta here represents the unknown parameters or the learnable parameters of the neural network. And mu theta x here is the predicted mean. However, something that we have to keep in mind is that if we want to predict the variance of output, because variance is always non-negative, we run into issues if we get a negative number. There are multiple ways to fix this problem. In my opinion, the easiest way to overcome this issue is, instead of predicting the variance directly, is to predict the log of the variance. And mathematically this works because then later we can compute the exponential of this number, and we know that the exponential and logarithmic functions are inverse of each other, so they cancel each other and we get the variance. And the nice thing about the exponential function, as you can visualize it here, is that the output of the exponential function is always non-negative. And therefore, in this case, we always satisfy the constraint that the variance must be non-negative. But the main point here is that instead of having a single point prediction, we will predict both the mean and variance, or the log of variance. And this gives us this normal distribution, which is parameterized by these two parameters. So the next thing that we have to think about is how we can train such models. In order to train PNNs, or probabilistic neural networks, that are defined as we just mentioned, the loss function that we use is log of variance plus this squared difference between the target y and predicted mean, and we have to scale this by the variance of the output. And also we have a factor of 1/2 or 0.5, which we can actually remove this if we don't want to, since we want to find the minimizers of this loss function. Therefore, we can multiply this by any non-negative or positive constant in this case. And this loss function is so useful and popular that PyTorch actually has a built-in implementation of these, which is called Gaussian NLL loss. If you look at the formula that PyTorch uses, is exactly the same as what we have here, except the fact that anytime that we have variance, it finds the max of variance and epsilon to just make sure that variance is never very, very close to 0, because that can run into issues given the fact that it also appears in the denominator. So these are usually techniques that like libraries like PyTorch and NumPy, they use for stability. But just to a little bit better understand what this loss function does, is that when the difference between y, the target, and the predicted mean, mu, is large, then the variance, or sigma squared in the denominator, also will increase to compensate for that, because the goal is to minimize this entire loss function. Therefore, the variance, which measures the uncertainty, should increase when the model is not accurate. However, this is a little bit more complicated given the fact that also we have the log of the variance as the first term. But remember that the log of the variance increases slower than the variance that is in the denominator. And therefore, that's like the key ingredient of this loss function on how it finds suitable values of variance for different inputs. The next slide, we talk about the derivation of this loss function if you're interested and if you have a strong mathematical background. If you don't want to go through this topic at this point, you can skip this part of the video and then we go and talk about the implementation. But the idea is that, usually when we want to find a loss function, we have to find the negative log of the likelihood function, which in this case, since we're working with one data point, that's negative log of the PDF or probability density function for the normal distribution that you can see here in these square brackets. And then from here, we have to just simplify this. We use the fact that the log of products is the sum of the logs, and in this case we get log of the first term, and then log and exponential, they're inverse, so we get negative y minus mu squared over 2 sigma squared. And from here we just have to simplify this a little bit more, and you can see that we get this 1 over 2 log of 2 pi sigma squared and plus this y minus mu squared over 2 sigma squared. The only difference between what we have here and the previous slide is that we have this 2 pi in the first logarithm function, and you can safely ignore this constant because it's not gonna change the optimization problem because we are looking at the minimizers of this loss function. But how does this work for implementation of these neural networks with the Gaussian head? So in this case, we can define a class, Gaussian MLP, because this is mainly for multi-layer perceptrons. And we're going to subclass this from NN.module from PyTorch. Then we define our constructor, where input dim here is the dimension or the number of input features. So for example, if we have, let's say, the energy efficiency data set, which is the one that we are using here from UCI, repository, then we have 8 features, and then the hidden sizes. So this for loop here is the one that makes sure that we have the suitable number of hidden layers, and then we use nn.sequential to make sure that we unpack this and we create this network. In this case, for example, if we have only 2 hidden layers, you can see that we get these 2 red hidden layers. And the most important part is that when you want to define the forward part of your model, remember in this case, we need to get 2 outputs instead of 1. We need to get the mean and log of the variance. And that's why we have to add that self.head, which is a linear layer that has the input dimension, which is the appropriate number depending on the previous hidden layers, and the output is 2, right? So in this case, we want to make sure we have 2 outputs for each input. And later, when you go to the forward part of this, you can see that we select the first one as the mean and the second one as the log of the variance. So in terms of implementing these types of networks, this is extremely easy. The main difference is that instead of producing 1 output, we do 2 outputs. The next thing is to define a function for our training loop. So in this case, we need to have our model. We need to have a train loader for having access to different batches of training data, number of epochs, learning rate. And as I mentioned, this is already has a built-in loss function in PyTorch, which we are using here, and n.Gaussian NLL loss. We want to make sure that we find the average error here that we want to minimize. So that's why we are using reduction equals mean. We set our optimizer to be the Adam optimizer. And also we need to have the loops over X and Y in each train loader. And as you can see here, since we are predicting the log of the variance, when we want to find or compute the loss function, we have to first apply this torch.exp to make sure that we find the exponential of log of the variance, which is the same as variance. And then we use loss.backward optimizer.step. So that's one step of gradient descent. And then for evaluating this model, now we need our test loader. In this case, we use torch.nograd because we don't want to change the parameters of our model. We just want to do evaluation. And you can see that, again, we find the mean and log of variance. So we have to, again, use torch.exp. We concatenate all these results, and then we return the mean of predictions, which we call here preds, and the variances. And also let's compute the RMSE, or root mean squared error, because that's a quantity we usually really care about. So now that we have our class and we have these two training and testing or evaluation loops, now we can define our model. In this case, because we're working with energy efficiency data set, we have 8 input features. We assume that we have 2 hidden layers of each size 32, and we train our model and we evaluate it. And you can see that here, the root mean squared error we get is 2.3. And the nice thing, since we are using this type of neural networks with the Gaussian head, we can compare the mean predictions versus true outputs. And hopefully this should be close to the 45-degree line, because these two ideally should be equal. And this shows you that our model performs relatively well. But then we can look at also predicted variance as a function of true output. And you can see that overall the variance is a small, meaning that our model is confident. But there are certain cases that our model is very unsure. That's like the key ingredient or aspect of probabilistic neural networks. Now we can understand confidence in predictions. And you can see that here this happens for true outputs that are between 20 and 30, and those are the cases that our model is not super confident. However, if you compare these results with state-of-art results, or more sort of like common results that you see like on the internet, you see that our RMSE is a little bit higher than like the commonly reported values. And this is in fact one of the main drawbacks of using the loss function that we saw. And this was the main topic of a paper that was published at ICLR, International Conference on Learning Representation, one of the most influential AI conference papers, that they talk about the fact that the loss function that we use is not super stable, and it has this issue that our model can just decide to increase the variance because it's in the denominator to artificially reduce the value of the loss function. But this is not ideal because we want to make sure that our model is faithful. So in order to tackle this problem, they propose something that is called beta-NLL loss function. So the idea is that, well, we don't want the model to just increase the variance because it's in the denominator to decrease the value of the loss function. And that's what we're trying to do because we want to minimize the loss function. So in order to tackle this problem, let's multiply the entire loss function or scale it by this variance raised to the power of beta. However, we have to be very careful, and there's a very small technical thing that we have to be careful here, that we don't want to this scaling factor to change the gradients of our loss function when we want to minimize it. Therefore, what we do is to actually detach this variance raised to the power of beta, this scaling factor, so that it appears in the loss function. It encourages the model not to inflate the values of variance, but at the same time, we are not going to change anything about the computation graph and the way that we find gradients. And overall, this helps stabilize and calibrate the predicted variance for each input. So the main difference here in terms of implementation is that now we have to define our own loss function. This is not built in PyTorch, but we can still use the built-in PyTorch loss function. And in this case, we use reduction equals to none because we want to make sure that we get the values of this NLL loss function for each input individually. And then we define our scaling factor, which is the variance dot detach, meaning that we want to detach it. And then we raise that to the power of beta, where beta is a given number. In this experiment, I'm using beta equals 0.5. Usually you can use something from 0.3 to max like 1. And then we multiply this scale by the values of NLL. And in this case, when we want to return, we return the average or mean of these NLL values across all data points. So in this case, if you repeat the same experiment, you can see that the value of the RMSE or root mean square error actually decreased from almost 2.3 to 1.3. And this is great because this means that this model on average makes better predictions. As you can see here, this is mean prediction versus true output. Also, if we look at the variance versus true output, before this went up to close to 30, now this is half of that. So now it goes to almost 15. And this is very important, right? So because this tells us now we are able to better calibrate or control those predicted variances. So overall, as you can see here, this is a small modification to the original loss function, but it has been shown in that conference paper and future papers or upcoming papers that actually is very effective in terms of calibrating predicted variances, and a very important technique to be aware of. I hope you found this video helpful.